The actual answer is we don't really know. If we actually built the fusion power plant and are operating it, the materials directly surrounding the device, our ability to predict about what their fundamental properties are, maybe a day of operation. And you want these to operate for a year. It's clear we're going to have to use the first fusion devices to actually give us some of the answers. But let's be really, really clever about down selecting choices through things like rapid assaying and computational modeling to actually get us to a point where our guesses are better earlier on.
Are there any recent advances in material science that directly found their way into fusion? For instance, graphene has been very studied and successful elsewhere.
Yeah, so graphene has come in through other means. Graphene itself doesn't really fit the bill. And it's because of this disordering business, right? Graphene works in general carbon systems because of the atomic ordering. So it's interesting. In fact, I worked a lot in graphite systems and so forth because they're excellent in many ways in a nuclear environment, but they suck from that point of view because they get so quickly disordered. So for example, if you take things like graphitic, high density graphite materials and silicon carbide is a little bit different actually, but graphitic materials that have very high thermal conductivity, which is very good. They're tolerant in lots of other ways, that they will tend to, their thermal conductivity will drop by a factor of 100 at fractions of a displacement per atom. So this would happen like in a day or two in a fusion device. It's like, oh shoot. Yeah, but there are things which are coming from a variety of ones. For example, high entropy alloys are an interesting one which are emerging, that namely in the end that's actually what the system is doing, right? Is that it's actually increasing the entropy in the material. So you actually start with high entropy so that it's already it's closer to its like final state, and so the relative impact of the neutrons of the displacements can be less. So those are ones which are coming. I think the really exciting frontier is the combination of rapid materials fabrication and assaying that are coming from automated techniques, and a lot of this is coming out of the material science community and my colleagues that work on this, that sit at that intersection, like our ability to go through like millions of permutations of different kinds of alloys, for example. In fact, I've got right now a PhD student who's doing that both experimentally and, of course, computationally. That's the other part where the blend of advanced and more rapid prototyping techniques combined with high performance computing are really at the frontier of what we do. This is the other one, along with and in fact, there's an experiment coming at MIT that's actually itself going to be going directly after these issues. We're actually going to have a new facility that's going to be right across the street from you. It's actually going to be in NW21. Oh, yeah, NW21.
Is it Nabisco? Nabisco lab? Yeah.
Yep. So it's the place where the fusion experiment was in the large concrete bunker which is there. And we're going to install a very high energy cyclotron to rapidly damage and transmutate materials.
What are the materials that you want to transmutate from and into?
There's some basic requirements in this, like you almost always start with alloys or some kind, or elements that have high thermal conductivity, because if they don't have that, you're toast already for the first wall materials because of this heat conduction problem. So you tend to start, and the other thing is that you don't actually want to, this is one of the other features of fusion, is that in the end what you're making is helium, so it has no radiological consequences. But if you put bad selections of isotopes in front of the neutrons, you'll actually make radioactive isotopes that can have features so that you would have to store them for a long time. We don't want to do that, right? That's one of the great features of fusion. We can design the so-called activation profile and the waste product profile of this through cleverness. So we tend to pick things which we call our low activation. So these are isotopes like vanadium, for example, which are have a very mild one. Anything that's lower atomic number, like silicon carbide, is outstanding on this. That's a really good one. But the actual answer is we don't really know. And here's one of the, if there's students watching this and you think about the frontier of this for fusion, is that it's also about what it means about its possible impediment actually in fusion. Is that approximately right now we have about maybe a day. If we actually built the fusion power plant and are operating it, the materials directly surrounding the device, our ability to predict about what their fundamental properties are, like thermal conductivity and strength and so forth, maybe a day of operation. And you want these to operate for a year. And the reason for that is because there's never been a working fusion power plant. So we have no empirical direct evidence. And there have been a few things that have come out of fission reactors, but even those are extremely limited about what they tell us, because the physics is different about what that is. Wow. And so one of the interesting parts of fusion is that it's clear we're going to have to use the first fusion devices to actually give us some of the answers about that. But then the other part is, let's be really, really clever about down selecting choices through things like rapid assaying and computational modeling to actually get us to a point where our guesses are better earlier on. And I think this is clearly one of the intellectual frontiers of fusion, which, by the way, will be really amazing because it's going to push material science, production, testing, modeling to its absolute limit, which is the other cool part of fusion, right?
It's extremely fascinating.
It tends to be right on the frontier of what you can figure out. Yeah, right on. But it's not impossible. We know it's not, and in many ways, it just has to get good enough that we know that we can use it in the system, because by definition, you're going to have to replace these components with some frequency. So what you just don't want to know is that it's unknown, right? About how it's going to react. We actually hope that facility is working by the end of next calendar year at MIT, and that will be a frontier science capability. Yeah. And it's a cool science idea, by the way, which also I came up with about 12 years ago in an undergraduate design class with a few material science people, and it was basically like, how do we get to what's a tool that we could use to start rapidly but correctly damaging materials in a way that a fusion device would? And the answer was protons, which is very non-intuitive, but it's a cool physics idea that, namely, if you get protons to be energetic enough, then they'll enter into the nucleus, and because what really matters is the strong nuclear force, which doesn't really care that much about protons or neutrons, because both participate in the strong nuclear force. You just need to get the protons energetic enough that they can actually enter into the nuclei, and then they'll start doing all the same crazy stuff that neutrons do. And that turns out to be around 30 MeV, like about double, basically, where the neutron starts. And it turns out high energy, compact cyclotrons, which are coming out for medical reasons, medical treatments, things like that, fit the bill. And it fits into our cell at MIT. We've just garnered some very generous donations, and we're going to install that, and we're going to start discovering. It's going to be cool. I think there's going to be a pool on this about which materials will fail the fastest in the environment. But the way I look at it's easy, but I'd rather know now than having to put it and having it fail in the first fusion devices. And what's interesting in this is that it serves not just a tokamak, it serves anything that's going to do about fusion, because they all face this challenge.
Yeah, it sounds a little bit reminiscent of when Edison was trying out different filament materials to see which one would last the longest. You just have fancier materials.
That is a great compliment, and hopefully we do it. So empirical exploring is always important in this, and having the right tools. And in fact, that's the other thing that's cool this proton facility does. It actually accelerates the damage by about a factor of 10 as compared to what you would actually get in a fusion device. So when you put that in for a day, it's like having it in there for 10 days in a fusion device. And as I said, that already takes you outside of where our present database is. So rapid assaying, trying, we're going to have to do things empirically, but I hope in a way that's even smarter than that. Because you just can't do it through pure empiricism, because there's too many combinations of, like, in fact, that's one of our PhD students right now. He's looking at just one. It's a tri-alloy that involved vanadium, and there's something like 10 to the 14 permutations of the alloy. You're not going to do those empirically, right?
So you need this dynamic design of experiment that keeps adapting. You use AI in assisting the design.
Yes. Yeah, the beautiful symmetry of AI with fusion is that we both probably need each other. You know,